Hi friends, in this session we describe Cauchy-Goursat theorem, a very important result in complex analysis with various theoretical and practical consequences. We know from the previous session that when a continuous function f has an antiderivative in a domain D, the integral of f set around any given closed contour C lying entirely in D has value 0. Now, we shall describe a theorem giving other condition on a function f ensuring that the value of the integral of f set around a simple closed contour is 0. So, let C denote a simple closed contour. Z is equal to Z of t, A less than or equal to t less than or equal to b, described in the positive sense, that is counterclockwise. In the counterclockwise, and also assume that f is analytic at each point interior to and on C. Then, as seen in the previous session, that is in the contour integral, we have integral over C f set dz, which is equal to integral a to b f of z of t z dash of t dt. Mark it as equation number 1, first equation. And it is f of z of t z dash of t dt. And if f z is equal to u x y plus I v x y and z of t is equal to x of t plus I y of t, the integrand on the right in expression 1 is the product of the functions, that is u x of t y of t plus I v x of t y of t and x dash of t plus I y dash of t of the real variable t. Hence, integral over C f z dz can be written as which is equal to integral a to b u x dash minus v y dash dt plus next term is plus I into integral a to b v x dash plus u y dash dt. Equation number 2. In terms of line integrals of real valued functions of two real variables, then integral over C f z dz can be written as integral over C u dx minus v dy plus I into integral over C v into dx plus u into dy. That is integral over C u dx minus v dy plus I into integral over C v dx plus u dy. This is our equation number 3. Observe that expression 3 can be obtained formally by replacing f z by u plus I v and dz by dx plus I dy on the left and expanding the product. Expression 3 is of course also valid when C is any contour, not necessarily a simple closed one, and f of z of t is only piecewise continuous on it. Now, we recall Green's theorem in calculus that allows us to express line integral as a double integral. That is, the theorem says that if two real valued functions, that is p x y and q x y, together with their first order partial derivatives are continuous throughout the closed region R consisting of all points interior to and on C, then integral over C P dx plus Q dy is equal to double integral, it is over R, Qx minus Py dA, where this Qx and Py are the first order partial derivative of Q and P with respect to x and y respectively. Now coming back to our main discussion, that is f is continuous in R since it is analytic there. Hence, the functions u and v are also continuous in R. Likewise, if the derivative f dash of f is continuous in R, so are the first order partial derivatives of u and v. Applying Green's theorem, we rewrite equation 3 as, by using that Green's theorem, we can write integral over C f z dz, which is equal to double integral over R minus Vx minus Uy dA, minus Vx minus Uy dA plus the other term plus I into double integral over R Ux minus Vy dA. Next equation number is equation number 4. But in view of the Cauchy-Riemann equations, we have Ux is equal to Vy. That we know Cauchy-Riemann equation, we have Ux is equal to Vy and what Uy is equal to minus Vx. The integrand of these two double integrals are 0 throughout R. So, when f is analytic in R and f dash is continuous there, we have integral over C f z dz is equal to 0. Next equation number 5. This result was obtained in early part of 19th century by the French mathematician A.L. Cauchy. Note that once it has been established that the value of this integral is 0, the orientation of C is immaterial. That is, statement 5 is also true if C is taken in the clockwise direction. Since then, integral over C f z dz, integral over C f z dz can be changed as minus integral over minus C f z dz, which is again equal to 0. Goursat was the first to prove that the condition of continuity of f dash can be omitted. Its removal is important and will allow us to show, for example, that the derivative f dash of an analytic function f is analytic without having to assume the continuity of f dash, which follows as a consequence. The theorem given below, that is without proof, is the revised form Cauchy result known as the Cauchy-Goursat theorem. That is, statement of the Cauchy-Goursat theorem is like this. If a function f is analytic at all points interior to and on a simple closed contour C, then integral over C f z dz is equal to 0. So, we move to some examples. The theorem is without proof, that is, proof is not mentioned in your syllabus. First example, show by Cauchy-Goursat theorem that for f z is equal to z square by z minus 3. integral over C f z dz is equal to 0, where C is the unit circle mod z is equal to 1. Solution. Here the only point where is not analytic is z is equal to 3, but z is equal to 3 is outside mod z is equal to 1. That is, function is not defined with the point z is equal to 3, but we have mod z is equal to 1, so 3 lies outside 1, and therefore f z is analytic inside and on mod z is equal to 1. Hence, by Cauchy-Goursat theorem, we have integral over C f z dz is equal to 0. Next example. If C is a simple closed contour given by the circle mod z is equal to 2, verify the following, that is without and second one with using Goursat theorem, Cauchy-Goursat theorem. First one is integral over C dz is equal to 0. Second one is integral over C z dz is equal to 0. Third one is integral over C z square dz is equal to 0. We verify third statement only, leaving the rest to the exercise. That is, first and second as exercise. I am going to prove the third one. That is, first one is without using Cauchy-Goursat theorem. Consider integral over C z square dz, where C is mod z is equal to 2. Here mod z is equal to 2. Now, on the circle mod z is equal to 2, z is equal to 2 e raised to I theta, where theta is in between 0 less than or equal to theta less than or equal to 2 pi, and dz is equal to, z is 2 e raised to I theta, so dz is equal to 2 into I into e raised to I theta, and then integral over C z square dz is equal to which is equal to integral, limit is from 0 to 2 pi. Here our z is 2 e raised to I theta. So, it is, here we have z square. So, 4 e raised to 2 I theta dz. Our dz is 2 I into e raised to I theta. So, it is 2 into I into e raised to I theta d theta, which is equal to, we can take 8 and I outside since they are constant. So, it is 8 I, we can take a constant outside, that is 8 I integral 0 to 2 pi e raised to 3 I theta d theta, which is equal to, on integrating we get it is 8 pi into e raised to 3 I theta by 3 I over the limit 0 to 2 pi. So, it becomes 8 by 3 into e raised to I 6 pi minus e raised to 0, that is 1, which is equal to 8 by 3 into 1 minus 1, that is equal to 0. Which is equal to 0. Next, by using Cauchy-Goursat theorem, here f z is equal to z square is analytic everywhere in the plane. In particular, it is analytic inside and on mod z is equal to 2. Hence, by Cauchy-Goursat theorem, integral over C z square dz is equal to 0. Next example. Since e raised to z and cos z are analytic function, by Cauchy-Goursat theorem, we can say integral over C e raised to z dz is equal to 0, and integral over C e raised to z dz, it is in the closed line, e raised to z dz, which is equal to 0, and integral over c cos z dz is equal to 0. Next we have to evaluate integral over c sec z dz, where c is the unit circle. Integral is again over the closed line, closed curve. Here it is unit circle, c is the unit circle. We can say sec x is sec z can be written as 1 by cos z. Is not analytic at z is equal to plus or minus pi by 2, plus or minus 3 pi by 2, etc. But all these points lie outside C. None lies on C or inside C. Hence, by Cauchy-Goursat theorem, we can say integral over C sec z dz is equal to 0. Next, we have to evaluate integral over C dz by z square plus 9, where this C is the unit circle. The solution is that the integrand 1 by, that is integrand is 1 by z square plus 9 is not analytic at z is equal to plus or minus 3i, but all these points lie outside C. None lie on C or inside C. Hence, by we can say by Cauchy's theorem, Cauchy-Goursat theorem, integral over C dz by z square plus 9 is equal to 0. Next example is, a non-analytic function need not satisfy Cauchy's theorem. That is, we have to show that integral over C z bar dz, which is equal to 2 pi I. This we have to show, where C is such that z of t is equal to e raised to I t is the unit circle. It is the unit circle. The function, here listen, f z is equal to z bar is not analytic, and hence it is false to say that integral over C z bar dz is equal to 0. Since C, that is z of t is equal to e raised to I t, where t varies in between 0 and 2 pi, that is 0 less than or equal to t less than or equal to 2 pi on C. Z bar is equal to, here we have z bar is equal to e raised to minus I t. We have z of t is equal to e raised to I t, so z bar is equal to e raised to minus I t, and dz is equal to, z is equal to e raised to I t, so we have dz is equal to I into e raised to I t dt. Here we have dt, dz, so I into e raised to I t dt, and hence integral over C z bar dz can be written as, which is equal to integral, it is from 0 to 2 pi, z bar is e raised to minus I t, instead of dz we can write I into e raised to I t dt. So, it is equal to what, 2 pi I. Next example says that a non-analytic function need not satisfy Cauchy's theorem. That is, we have to show that integral over C dz by z is equal to 2 pi I, where the C is of course z of t is equal to e raised to I t is the unit circle. Here the function f z is equal to 1 by z is not analytic at 0, hence it is false to say that integral over C dz by z is equal to 0. and also the verification, that is the verification integral over c dz by z is equal to 2 pi I, it is left as an exercise for you. Next example is about analyticity is sufficient but not necessary to get integral over c f z dz is equal to 0. It can be verified that integral over c dz by z square is equal to 0, where c is the unit circle. This does not imply that f z is equal to 1 by z square is analytic at every point inside the unit circle. It can be seen that the function f z is equal to 1 by z square is not analytic at 0. Next example is that using the integral over c dz by z plus 2, where c is the unit circle mod z is equal to 1. And it is to show that integral 0 to 2 pi 1 plus 2 cos theta by 5 plus 4 cos theta is equal to 0. That is, here we have to find the integral over c dz by z plus 2, and of course, and we have to, here mod z is equal to 1. And we have to show that integral 0 to 2 pi 1 plus 2 cos theta by 5 plus 4 cos theta d theta is equal to 0. This we have to show. Here mod z is equal to 1 is a given curve, and we have on that curve z is equal to e raised to I theta, and theta is in between 0 and 2 pi. Again dz is equal to I into e raised to I theta, and z plus 2 is equal to 2 plus e raised to I theta. Hence, integral over c dz by z plus 2. Integral over c dz by z plus 2 is equal to, it is from 0 to 2 pi. Our dz is I into e raised to I theta divided by z plus 2 is 2 plus e raised to I theta, or you into d theta, or e raised to I theta plus 2, which is equal to, we can take I outside, I into integral 0 to 2 pi cos theta plus I sin theta. Here we have e raised to I theta remain, it can be written as cos theta plus I sin theta divided by cos theta plus 2 plus I sin theta. Here we have d theta, okay, which is equal to, here we can put a bracket, which is equal to I into integral 0 to 2 pi cos theta plus I sin theta into cos theta plus 2 minus I sin theta by cos theta plus 2 whole square plus sin square theta. That is, we are multiplying with the complex conjugate of the denominator. Here we have cos theta plus 2 plus I sin theta multiplying with the complex conjugate, that is cos theta plus 2 minus I into sin theta. So, it becomes, which is equal to I into integral 0 to 2 pi, what remains? On the numerator we have 1 plus 2 cos theta. In the denominator it is 5 plus 4 cos theta d theta minus the other term minus 2 into integral 0 to 2 pi, it is sin theta by 5 plus 4 cos theta d theta. Equation number 4. No, this is our equation number, first equation. But by Cauchy-Goursat theorem, we have integral over c dz by z plus 2 is equal to 0, as 1 by z plus 2 is analytic in and on the circle mod z is equal to 1. Mod z is equal to 1, it is just like this, that is integral over c dz by z plus 2 is equal to 0 by Cauchy-Goursat theorem. Equating the imaginary parts on both sides of 1, we get By equating, we get it is integral 0 to 2 pi 1 plus 2 cos theta by 5 plus 4 cos theta is equal to nothing but 0. Next equation, or this is our answer. So, in this session we discussed Cauchy-Goursat theorem and we have done so many examples using that theorem. Hope you enjoy the session. See you next time. Till then, take care.